Hello, my friends of Hatari Labs. My name is Saul Montoya. Please welcome to this tutorial. In this tutorial, we are going to study the river-aquifer interaction in a, eh, on a using a geospatial groundwater model that has a Voronoi mesh. Okay, so what we are going to do now, we are going to you are going to receive this in the description of the video. Um, some data that is of a river that has some wells, that has a recharge zone, and that has a general head boundary, because there is also, besides of the well, there is also the regional flow. So we are going to simulate all of this in a groundwater model. So let's start. For this simulation, you're required to have a geospatial content environment together with some package. So there is a tutorial for that it will be added on the description of the video. So say conda activate. So we are going to activate GeoHatari, that is my environment. Okay. So and say here cd documents cd river. Okay, so and then here we are going to launch Jupyter Lab. Mhm. Okay, so you are going to find here the executables, that is only MODFLOW 6, the input file, that are the raster and the shape files, the notebooks, that is the only one that we are going to cover here, the out, that is where we are going to store the model, and some scripts here. Okay, so here let's go to notebooks. Great, and restart and clear our outputs. Okay, so let's import the required package. So we have basic package as OS, JSON, pandas. Then we have geospatial data as geospatial package as geopandas, rasterio, shapely. And then we have as well matplotlib, flowpy, and we also insert the sys to our folder in order to import this as a package. Okay, so we just run it. Okay, and then we define mesh. So we create the mesh object, we define the parameters, and then we add the limit, that is the limit of the model. And then in order to define our mesh, we are going to use the layers, and the layers will be the wells and the river. So let's run it. Okay, so in this case we are going to use um, 5 stages. So this is from 80 to 10. Okay, you can play around with this, and this really, how say, advice. I mean, we advise you that you play around with this, because this will tune the discretization. Okay, so and then here we are going to generate the point array, and we generate a point cloud, and then we generate the Voronois, and as well we got the Voronoi regions, but we also have some preliminary data related to buffers and well, other material that was that could be helpful to see how the Voronoi mesh has been made. Okay, so okay, we don't like to have to ignore warnings, but there is a problem here, because we are working here with different versions and their content environment. So there are some incompatibilities that appear as warnings. Okay, those are warnings, but there are a lot of warnings. So in order to prevent that, we have ignore the warnings, and then we open the Voronoi mesh, the river, the general head, and the well, and then we have added open this as a with GeoPandas, and then we have plotted in because we want to show you how they are. Okay, so this is the general head boundary, this is the river, and these are the wells. Okay, and then you see the discretization. Okay, so we are going to generate the Voronoi grid, I mean the Disv parameters. Okay, and then uh, for the Disv there is a list of vertex cells, IDs, and so on, and then we can from the grid props, that is a dict, we of the different keys of the dict, we are going to have the cell 2D, the vertex, and so on. So if you want to see an extract of the cell 2Ds, here you will see the index of the cell, the coordinates of the centroid, the number of vertex, and then the vertex IDs. Okay, so let's define the aquifer geometry. So we are going to open the ADEM. Then we do a list of the centroids. Okay, um, and then here we have the three layers, where here we uh, we uh, where here we got the elevation of n top. So this is elevation 0 for E elevation in enumerated elevation. Okay, great. So, and then this is just for the sample of the centroid, because centroids are the centroids. Okay, so here we got the elevation for the sample. Okay, and then we define this as a numpy array, and then we have the bottom, that is a zeros, that will be um, the set bot is a zeros of number of layer and number of cell per layer. Okay, the aquifer inferior bottom is 120. The aquifer medium bottom is this formula, and the other is that formula. Okay, so and then from that you can get the bottom of layer 1, layer 2, layer 1, 2, and 3. Okay, we then open a MODFLOW 6 simulation, because in MODFLOW 6 you have the simulation and then you have the groundwater model. So we create a simulation, and a simulation can run many models. However, all of them need to have the same temporal distribution. So here we define the temporal distribution of 11 stress periods, where the first stress period is in steady and the rest is on transient. Okay, and then we define the solver for the simulation, and then we create our groundwater model, and in our groundwater model we create the Disv option, that is the discretized by parsecs, and as well we define the initial conditions. Okay, so we define the steady and transient parameters, that is steady is kx, ky, and kz, and while in transient is the storage. Okay, so we gave a value for all the model of a specific yield and specific storage. Okay, okay, great. Then we are going to plot the grid with the uh, Flopy utility, so that's why here we use the Flopy plot map view. Okay, and as well here we can do a cross section. On the evapotranspiration package, we are going to use evapotranspiration as array, and here this is the value of the evapotranspiration. On the recharge package, we intersect we create a intersect object, and then we intersect that with the recharge zone. Okay, and then we can run the plot the selected cells for you to see. Okay, these cyan cells are the cells that are intersected between the recharge zone. Okay, and those are the ones that will be applied with recharge. Okay, okay, and then we create the stress period data, and then we apply this. As well, we work with the well data because we open the well, we add the wells, then we create a multi-point, then we intersect the wells with our grid, and then for the selected cells we apply the pumping rate. And then as well for the river package, well, if the because we have is a general head boundary, so if the x is less than something, it will be applied with a head of 55, and if the x is higher than that value, it will be a, a head of 90. Okay, then we define the output and run the simulation. Okay. Okay, they told me that is still going. So I'm going to do kernel, restart and run cells. Let's see if this works. Or maybe it's a procedure that is on the... Okay, now it has run. Okay, and then here we open the heads, and then here we have the head distribution. Okay, so this is the head distribution, and this is the river. Okay, so here we see the general head boundaries, and then here we see the impact of the wells, and as well here we see that with a color map. Okay, and then we can see this on a cross section. Okay, so something important to mention is that we are working with Voronoi grids, that the model is entirely geospatial, and that we can do more interaction with the output data, because and then we can do cross section based on alignment as well. And that's it. So uh, the input file for the model are in the description of the video, and you are entirely invited to follow these tutorials and as well the codes that we have done to create the Voronoi meshes. Okay, so far that is everything for now, and hope to see you in coming tutorials, and as we say, viva el software libre. Have a great day. Bye bye. Bye.